start with an introduction, then we have a list of presentation. Yes, for the recording. Okay. A list of presentation of the people involved, PhD students and postdocs. Some of them are now postdocs. They were PhD students like Rami and other people that you all know, but I will introduce them later during the presentation. So we intend to close around 16:20, but I would like to stay more or less in a fuzzy way with the Gaussian propagation, with the with a little bit more, a little bit less on the edge, because I think I would encourage any discussion if there are. Okay, not just boom, boom, boom in one direction. I would rather have discussions.
The closing discussion starts at 16:20.
Yeah, no, but also if very often if you have something you don't stop asking. It's better to ask in the moment, and maybe if something takes too much time to divert it at the end. But please do interrupt whenever you want and can. All right, so I use this citation very often. Okay, in all things of nature there is something of the marvelous. And if you look just in nature and for example birds. They've inspired scientists for centuries, and as I say all the time, Leonardo da Vinci couldn't leave it out of the presentation as an example of that. And robotics is the science of integration and an embodiment of technology, the physical world. That's as a background, I grew up as a control theorist, doing physical modeling eventually, but driven by robotics, and this is why I think it's very important, because people undermine the importance of robotics as a whole. And I think there is a need for a powerful methodology to model really and control any kind of complex multi-physical systems. A robot is just more than a bunch of pieces of rigid stuff connected together, as the birds will show. And then flapping flight is a clear example of this need. So what I want to talk to you is really about, try to give an example on, what is port-based thinking. And of course, I don't need to do it for Arjan, okay, and other people that are here in the audience, but I want nevertheless to try to give intuition also about the kind of mathematical tools we use, because I think this is the core of the whole thing. And that has to do with exterior calculus, which is actually, the more I've even learned it in my engineering education, the more I'm working with it, I realize that why it is not standardly taught at every basic course for engineering. It's surprising, very surprising. And then we'll have more practical experimental results, which are very nice. Actually, a recent campaign that we had, which is very promising. The publication are not there yet, but these are very good results. And then just speculate about what I want to do next. So this is the robotic bird that we started off with, which was actually developed by Robin Moening. It was how do you call it? An hobbyistic in flying. How do you call it? Modeling aircraft. And with insight and trying out and reasoning about this and the insight that he had, he managed to do the first version of this bird, which was just far above any performance that were out there. And at that time I was working with the Mythbusters for something related to flapping. I got in contact with Nico, who was the CEO of the company, who took over the patent. And then from there, the whole story started. And I was intrigued by the thing, because, why does it actually fly? What can we do? And of course, with the background of Port-Hamiltonian thinking, I thought there is much to be done here in this direction. And of course, we also changed a number of things. We put, for example, the possibility of flapping and stopping. So we've been doing, on a practical side, kind of collaborating with the people working on that. But I was really triggered about the possibility to look at, please come in.
I'm just curious.
Okay. So this is so the bird got a lot of attention. So we have a number of recognition on that. The tech transfer award from Twente to Cliff Solution. We had a paper which was the best paper award, in which kind of tried to describe how things conceptually seem to work, and a number of things that we did in the past. And you know, from a 2D point of view, these are some numerical simulations that were done. One of the driving ideas is the fact that you know, normally normally aircraft, you don't want to have flow separation, right? Because that's not very good. But actually, in birds, you create these vortices that are inverted by moving that are shedded up and down, and then you create this kind of jet stream that gives the propulsion to the bird. This is what it seems from some simulation and insight in certain cases. But you know, why and how does it really work is the question, which is of course more from scientific point of view. Why is it? And only the understanding that we can, if we understand that really systematically, we can improve it and make an even a better bird, okay, or something else by that knowledge. And as Wittgenstein, who's a famous philosopher and a mathematician, said, what we cannot speak about clearly, we must pass over in silence. And this is a sentence I like very much, because nowadays, you know, in politics, they should start reading these things and then talk about stuff. I think that if you want to talk about flapping clearly, we must first use the language and understand. And I think that physics and port-based anywhere methods with proper mathematics is the only way to do it. So I was fortunate then to write this vision on, and got this huge amount of money, which I say it all the time. It took me practically 2 weeks writing, and I got, so the shortest it ever took from writing, and the biggest amount of money I ever got. So the ratio was very good, and I didn't believe my eyes when I got it. And if you want to know more, there is this article which gives a kind of overview from the vision that was defined. This is the page where you can go if you want. There are more informations that you can read there. I was fortunate to set up what I call a dream team. The people here are all the people that have been working on this, let's say the PhD student and the postdoc, because of course I've been collaborating with colleagues. And in the meantime, I also got, thanks to also the hard work of a number of people here, especially Alex, an ERC proof of concept, which is something else. I will not talk about it. Will you say something about it? No. But we have a patent on printing, which is actually pretty cool. And I am now, as far as this is actually something I also talked with Vasilis, a way to stochastically analyze it. And we are very close, I think. I really know how to do tomographic analysis of the printing. So there is very cool stuff, practical and theoretical stuff. And then later, Yi actually took a PhD in Delft with the market, who was there at the back. And Yannick have joined a bit later during the project. So knowledge, what is knowledge? Knowledge is, you know, what Aristotle was the techne and episteme. Episteme is the reasoning kind of more what you could connect to rationalists like, you know, Plato, and more recently Descartes, and the empiricist, more experimental work, more connected to Aristotle and John Locke in the current time. And I think that if you want to do good engineering, you cannot just work on the top. You need to do both. Okay, so you need to do the conceptual reasoning, at least in academic level, and the practical one. So the real and abstract world go hand in hand together, and I think that you cannot do good things in the real world if you don't have an abstract world. And in that respect, Fredrik gave a wonderful talk about the history of physics. You know, this interlacing of, you know, fundamentals and practical things that brought physics where it is today. So I will go more on the conceptual side, and there will be more talk later. And there will be also some more work explained in the end more on the technical side. So the idea is that, you know, we know more or less, this is the bird, so you have a rigid body, and then we know how to model that very well in our context. But then what is very nasty are the wings, of course, because the wings are deformable, are 3D deformable elastic bodies. And not only, of course, the wings move in the fluid. And the fluid is a very complicated physical domain, which follows Navier-Stokes equations. And how the hell do you connect something which has the PDE defining elasticity, a PDE defining fluid, and there are two PDEs connected, and not only the boundary of the two PDEs is moving itself also. It's very complicated, right? That was the vision, said we need to find a way to do it, and actually we did. And in this endeavor, we found out that we really needed some new concepts, mathematics in this context. And this is Greek probably for most of you, but this is what are called tensor value differential forms. And I'll try to give you an intuition of what this is all about. But this is what was really an insight we got. It says we really need this stuff, otherwise you cannot do this. So the conceptual things we wanted to tackle, this was the vision I had originally in the project, and we nailed it one after the other, and I'm very, very happy about that. So first was to understand in a completely geometrical sense a possibly curved coordinate-free way to model fundamentally fluids, okay, and in Euler context. And that was actually the work of Rami's PhD. That also handled was a second part, giving attention to model as an advection. So basically the kinetic energy structure is the one that moves things around, and then all the rest, like pressure and entropy and all these things in the fluid are moved by this kinetic structure. Of course, it's obvious if you talk like this, but to formalize it, it's a different story. And then we extended this to full Navier-Stokes, and including bulk and shear viscosity. And then is where we realized that we needed this new structure I just talked about. And this brought to two publications in Physics of Fluids. One really more Navier-Stokes, and the other one which actually extended this to Fourier Navier-Stokes, that was led by Federico. And actually we got very cool things which needs much more work, in my opinion, because we gave a different view to look at entropy and advection of entropy in fluids, which I think there is a lot much more than what we did. And then the point was moving boundary, because as I said, the wing moves, so you need to move these two PDEs. How do you handle that? I think we nailed it, and from a continuous point of view, it's clear now what is going on. On the numeric side, we still need to do some work, but we know how to tackle that. And then, of course, you want to do numerics. And then we were inspired by the work in Delft, that was done in Delft by Mark, Arthur, and Yi. Where is he? Oh, he's probably finishing the presentation. Oh, there's he. I didn't see you. Which brought to really bring this dual field things that I will say a few words about. And then I realized by doing that, actually continua, I really thought about what is the structure of continua in general. And I realized that there is a principal bundle structure, which is something, a concept in mathematics which gives enormous insight. And I will try to explain in intuitive terms what that is. And then this was also used in the work which was led by Rami on my opinion, the nicest work on elasticity out there, because it's a comprehensive work which shows also a lot of work done by, for example, Jerry Marsden and other people. It makes it much more precise. It shows that certain statements were not correct, etc., etc. So, and PyHam, you will talk about, because Yi is doing a phenomenal library, writing a phenomenal library for that. So what is about port-based thinking? Einstein said, Einstein, of course, about the one of probably the most influential and smart people that we know. And he made these statements, the complete statement is down, but basically it's a classical thermodynamics, the only physical theory of universal content, which I'm convinced will never be overthrown. So the concept of thermodynamics, energy, entropy are really the fundamental driving concepts that very likely will stay and will be leading all the rest. And in fact, Porte-Hamiltonian system theory is trying to find a structure that preserves the conservation of energy in your modeling process. Okay, so energy transfer and powers as basic topology of modeling decomposition. Now, you may know this picture. This is Raffaello's Academy. Okay, and in the Academy of Plato there was this sentence which atheometritos midis Isito, which means let no one ignorant of geometry enter, which is not specifically meant for geometry itself, even if I like it because I love geometry, but is meant more broader. But I do think that geometry has been completely fundamental in everything which is done here. And what is Port-Hamiltonian system theory, rather, with respect to the more classical Hamiltonian system theory? Well, I think it's the physics of Lego. Okay, so it's a way to really model things in a completely open way, like a Lego block, that you can attach to any other Lego block. If it has the same connection as the same port structure, you can attach, and you can build bigger systems. And they are meaningful on its own. So if you have a PDE with open boundary, that's a Lego block. If you know how the port, you can attach it, you can model it. And this is very different than what is normally done. Okay, so normally, from a mathematical point of view, in Hamiltonian theory, Lie-Poisson structure and in reduction is used. This is really a structure that was introduced by Arian and Bernard, which is called the Stokes-Dirac structure. It's really different because Hamiltonian theory goes mostly top-down. So you basically take the whole system and then the energy and you put it down inside here. You put the piece of Lego. You want to decompose and then to know how to attach those pieces of Lego together. And it's open. And you can have open boundaries. So all the things which you need for doing Lego-like kind of things can be done. And also dissipation. Dissipation is just a specific kind of Lego which you can attach, and it is a different structure. And there's a lot of work done also, especially by Arian, also on this thermodynamical stuff. So let me try to give you my view what is the core of everything here. The core of everything is, now I will do it top-down, but usually it's done the other way around. If you have a physical system, what is driving about the physical system in the classical sense? Because it turns out that this can be generalized also in another sense. You have a physical system. What is, the physical system has a certain energy content. Okay, that's the energy the system has. If you want to decompose, okay, we do a decomposition because of engineering way of decomposing. As Descartes says, if you have a complex system, to understand the region on the system, you want to decompose it, understand the parts, and then unite them. These two parts will have on their own, a certain energy content. But now the question is, how do you describe the structure in which these two parts of the system interact? That's the question. Okay. Well, you know that at least if you want energy conservation, you want that the sum of these two energy is this energy, right? So you want something that preserves that. And so if you look at that, it means that the power transfer should be such that the energy, the power that goes out from here goes up here or the other way around. So there should be an energy balance there, right? And the question is, furthermore, that we know that in physics everything is bidirectional. There is no way that one system can have an effect on another system without the opposite. There is no way. You cannot do that. We know that in physics. Action-reaction is just one example of that concept. Okay? So let's call them E and F, these two things. And I don't know what they are. I don't know what the mathematical structure they have. I know nothing. Okay, just say that E is something that is the influence that this part gives on this, and F is the influence this part gives on this. Okay? Now, the question is, what is the nature of these two guys? Okay. Well, and it turns out that what we want, in what I said, is this, right? So it turns out that the perfect mathematical structure that does exactly describe this is duality. Duality is, more than I work in this stuff, the more I realize that is probably the most important concept in physics ever. Duality. Which is basically saying that what a vector space, you probably know, but incredibly enough, people, an engineer, they don't say what a dual vector space is. You just think that it's the same. It is not the same. Okay, dual vector space is a space of linear operator that eats one vector and gives you a real number. The real number is power in this context. Okay, and you could think about, a velocity is a vector, a force is a dual vector. It's not a vector. I don't have the time to go into it, but a force, mathematically speaking, is not a vector, is a dual vector. Okay, so a force would belong to this set. It's not a set, it's a vector space, and velocity would belong to this. So these are kind of force-velocity pairing. Okay, but it turns out that this is much more than just in this example. This can be any vector space, and this can be any dual vector space, which is dual to that. So if you have a vector space, whatever that is, there is a unique dual vector space associated to that. This structure can be used for scalar system, vector system, multi-body, fluid dynamics, anything. It's just this. The only thing you have to identify what is V. Because if you know V, you know V star. And you have everything. This is the core idea, I think. And it turns out, by the way, so you can have different kind of V's. So V, we know electrical circuits, current and voltage. In multi-body dynamics turn out to be Lie algebras. And in infinite dimensional, it turns out to be forms. I will say more about this. And we found out that the general case of continuous mechanics, you need something even more in order to be able to describe strain and other things. It turns out, as I was just discussing during lunch, that this is actually what I said is much more, it goes even further than this, because I realized that this is actually true for any decomposition in which you have a symmetry. So, because energy is something you conserve, and by this decomposition you have a certain depending on time, and this is a concept that can be generalized for any kind of symmetry. And we're working with Fredrik on something related to that. And then you can just change the notation and say, if the value of the application of the force and the velocity is positive, that is power. Does the power go in this direction or this direction? That's an orientation issue. Okay? You give it an orientation notation, bond graphs. There you go. That's what bond graphs are all about. Okay? And this property defines any possible imaginable vector space. So this is true for any vector space. The only structure, mathematical structure that I use is the fact that what I call flow is a vector space. And I don't care about dimension, I don't care about anything, it is a vector space. But then I have to think abstract, and that's why I say engineering should give more attention to this, because if you think abstract, you can generalize this to PDEs. Okay, now, I want to say a few things about the continua. So by the way, this is, for the mathematician in the audience know the first one. I think the second one was your sentence, the second one, right?
Yeah.
So what it means, matrices, right? A matrix. So a matrix is just a numerical representation of something which is called a tensor, which is the real thing. Okay, and when you work with linear spaces, basically you should not go and write a matrix unless it's really necessary, because all the concepts you want to express should be independent on the base you choose. Because if you choose a base and you do something, you should then show that was independent on the choice of base you did. Okay? So a gentleman only chooses a base if he must. And this is a mathematical, I don't know who said it first, but this is a non-mathematical statement, right?
Well, no. That I heard in a Cambridge lecture.
In a Cambridge lecture. But then, of course, for gender balance, Frederick came up with a second, which is a lady must never go to the cemetery, because in the cemetery, what is a matrix? One of the lecture of a matrix is a symmetry of numbers, Okay, that's what a matrix is, and it was in one of a fantastic lecture that Frederick has on YouTube. That's what I wanted to write it. So I want to give you the essence, in the sense, no numbers, geometry. Geometry is what it's all about. And this is also used and expressed and explain a bit more in this paper. So what is the geometry of continua? We have an ambient space. The ambient space is where we live. And very often, if you take any work on elasticity, it's completely mixed up. I'll say this more. Let's say not everything, but because there's been a lot of literature in that respect. But you need to make a conceptual distinction between the space you are living in, which is the space we are living here, which has a metric structure. It's an Euclidean space. Okay, you can in this space have measure stuff. You have orthogonality and all these kind of things. This is the ambient space we live in. And then you have to decompose it and separate it with something which is the matter. And then the matter is a different space. Very often it's just considered like, no, it's a different space with a different structure. And matter is again a manifold, again a space. And as the only structure it has is the density of matter. That's it. It does not have any inner product, doesn't have any Euclidean. No. Matter has density of matter, and space as geometry. And then what you do by studying it is you put matter in space. Okay? And when you put matter in space, you embed matter in space, and you get a new thing, which is, called, it's the Lagrangian, is the space of all possible way you can put this matter in space, basically. Okay? And this point in this space is a possible way how I put matter in space, basically, okay? So if I have this point, I can have a curve of this point. It means if I have matter in space, the way matter moves, of the forms or whatever, that could be a fluid, can be anything, is just a curve in this infinite dimensional space. This is an infinite dimension because I have infinite way that I can put a piece of matter in space, okay? And then I can also think about velocities, okay? So this point, the velocity there, is actually a vector field on how all the matter can move in space. But by this conceptual separation, I get a lot of advantage. I then can, of course, take this vector back, what is called a pullback, on this domain and have basically the vector fields of the matter. So suppose I have a stick, a cylinder, a deformable piece of rubber. Okay, it's not in this ambient, it's in a different world. I have this piece of rubber, okay? And then I embed it in the space we live in. And I start deforming, throw it in the way, but I don't know what it's doing. And I look at these things, it's always not moving at all, but I see vector space on these things. This gives an idea of what is going to what is happening there. Okay, because if nothing is moving, no velocities. Okay, if somebody is deformed, I will see velocities that give me that information. Or I can put it forward. That would mean that would be the velocity of the points that I have there. Okay, this is what is called the Eulerian interpretation. This is called the convective interpretation. And this is what is called the Lagrangian interpretation. These are known terms. But making this split makes this very importantly. And then what you see, and this is something as I showed that I realized, that this space has what is called a principal structure, principal bundle structure. So this space, you can decompose this space in what is called a fiber bundle, which basically says, you know, if I have a deformed thing, I can, of course, rigidly move it anywhere, right? It's obvious. Okay, and this is a completely different thing that I start deforming it. Because if it's deformed and I move it everywhere, okay, I will moving along these lines, which are called fiber in a principal bundle structure. But if I stretch it around, it will have a component of motion which is not along this line, okay, which is got off this line. And this is what a principal bundle structure is. And it turns out that this is precisely, this base space is the correct way you should talk about deformation in elasticity. Okay, it's you know, there are different kind of tensor in elasticity, you know, Piola, Cauchy, you name it. You know, they are all the same. It's just that you think, you know, what are you talking about? It's exactly the same. It's just related to this space. Okay? And then you can define elastic stress, you know, elastic energy, you can define as a function on that manifold. That is clear when you understand this picture, what's going on. And it turns out that you can define also, this is also in this paper, a connection, which is another mathematical structure, which allows them to decompose in a unique way the vertical part and a part which is called horizontal in this plane, which turns out to be, okay, the part which is actually not along the rigid body motion is called is the rate of strain, okay, which is known in mechanics, okay, but the correct geometrical invariant way of writing is like this, which is a Lie derivative concept. And then what is very important is this formula. This was the thing that actually let us understand that what was going on, because this thing is symmetric. This is what is the vorticity, which is asymmetric, but this is symmetric, and this is basically a possible vector. You see, this is a possible vector, okay? And then you have something which is the vorticity, which is a rigid body motion, different than people think. It's kind of rigid body motion of the fluid around that rotation, in some sense. And then there is the part which is more the stretch of the fluid, okay? And in this paper, actually, it even shows that by screws, by infinitesimal screws, you can define this. It gives all the geometric interpretation of that. And this is the total picture. You have basically the convective, the Lagrangian, the Euler representation. This is, you know, the velocity, convective velocity. This is the Eulerian velocity. This is the Lagrangian velocity. And thanks to this insight, you can really understand how elastic media work. You can see that you need, due to this symmetric part, you need a new concept which is able to describe this difference that requires something symmetric, which is not what you normally have in form. I will tell you more about later, which has to be antisymmetric in order to do integration. Because integration, which you learn in RN, integration is something that is mathematically very clear and is an object I will define later. Okay? And vorticity is not, as often thought, a source of dissipation. This is nothing to do with the source of dissipation. Okay, what a power port is, basically, it follows the idea of Heaviside principle. What this is nothing else than the continuity equation in strong form, which basically says that the density of energy in space is equal to the flow of energy going in the part of space or going out of the part of space, plus a generation of energy or a dissipation of energy in that space. It's just a continuity equation of energy, which is used in different things. But for energies, that's the way it looks like. Okay. Furthermore, energy can be stored elastically, can be dissipated, okay, which is not right what I'm saying, because energy cannot be dissipated for the first principle of thermodynamics. Okay. But it can be basically irreversibly transformed to heat. That's the proper way of saying. And then, shape in the sense, can move it, and the dynamics, how energy moves around, is actually the source of dynamics in the first place. This was a book that that kind of reference for Port-Hamiltonian system theory, which was the end deliverable of probably the nicest project. Then a number of people here, I see two of the people that were involved at that time, Paul, working now in Twente and Arjan, of course. And basically says that every physical system, you can decompose it in this way, where these are ports, this is storage, this is irreversible transformation to entropy, for example, and so on and so forth. So what is the geometry of power ports? A bit more detail. So as I said before, a vector space and a dual of a vector space. So our signals, a function of time. So time, you give if something from a time give me velocity, for example, from time give me a force. Okay, but this is more general, okay? Because this is the case in finite dimensional. What is in infinite dimensional? Okay, so in infinite dimensional case where PDE starts to play a role and fields start to play a role, and this is more general than just what I said. Electromagnetism, anything which is a field can be put in this context. You need to talk about the space, because a field is something which is distributed. So a manifold concept is basically, am I called as a manifold, could be this volume, for example, and this would be the boundary to this manifold, which is the boundary of that volume. Let's say a sphere, the content of the sphere, and what is around it. And you want something which is independent on dimension, which is independent of coordinates, which is applicable to all physical domain, and possibly even curved. Because why? Because you think everything is flat, but then not everything is flat. Okay, if you want to study fluid dynamics of meteorology, I'm sorry, but the Earth is not flat. If people think that's the case. Okay, and the fact that it's not flat has a complete influence on how the fluids move around the Earth. Okay, and what you need is exterior calculus. And to do it properly in this duality framework is exterior calculus and differential form. So I don't have the intention to give you, I'm already out of time right now, more or less. No, I have more?
Yeah.
Okay. But
you can take like one more hour.
So what are these? So it's not my intention, some of you know it, some of you never heard about it. I'll try to give you an intuition at least why you would think about going here. So first of all, the history. This was actually started from Grassmann, and then Cartan made it really the beauty that it is now today. Okay, and it is the generalization of the concept that a function, if I give you a point, I have a function on a space, okay, what is a function in that point is the value of the function in that point. Okay, you can generalize this concept by saying, is there an object that I can evaluate on instead of a point on a line, or is it an object that I can evaluate instead of the line on a surface, on a volume, those are forms. Okay, it's just like a function. You evaluate a function of a point, you evaluate a one form on a line, you evaluate a two forms on a surface, you evaluate a three forms on a volume, and a four forms in a four-dimensional space that kind of space-time could be, for example. Okay. All right. So what is it? So a K form, which I indicated like this, belongs to this space here. Okay, is completely antisymmetric, and there are reasons for that because that's just the way volume works. Okay, it's basically something that eats K vectors and spits out a real number. Okay, so a one form in a point, for example, you give him one vector, spits out a real number. That's a force, for example. A force is a one form. Velocity, okay, the one form eats the velocity, spits out power. That's what a one form is. Okay, a two form eats two vectors. If you have two vectors, you can define a parallelogram. It's basically something that associates to that parallelogram a real number. The area, for example, of that parallelogram. This is the idea. Okay, and it goes to scalar values now so far. So basically what it is this is kind of what is called a topological pairing. You give me a form, a K form, you give me a domain, a K-dimensional domain, you pair them. That's what integral is all about. You haven't learned it like this if you had basic course in engineering, but this is what integral is. Okay, it's something that's a pairing between a domain and this object which is called a form. What you write as dx wedge dy, well, that's a form. That's what it is. Okay, and this pairing is basically evaluate that there. So a function evaluate in a point. Okay, a one form evaluates, you evaluate on a line, a two form, as I said before. Okay, so it's nothing else than the generalization of a function. That's what it is. But it's the right way of doing, which is completely right, it's completely independent. It's not dependent of metric, because if you stretch space, still works. It's a topological pairing. But there is something more, because if I give you a point, I cannot orient a point. If I give you a line, I can orient a line. I can say the line goes like this or goes like this, right? I can give an orientation. If I give you a plane, I can orient a plane. I can up or down. And so you can do for any domain bigger than 0. So the question is, what if I change the orientation? No? And then you can define two objects. You can define an object which is called a form normally, which basically says, well, if I invert the orientation of the domain, does the value invert? Then I call it a form. Okay, that's a geometric. But also you could say, and it is a reason which, and this is something which is not, the important Hamiltonian setting is not being clearly stated, but it's fundamental that if there are situations in which you invert the domain and you do not want to have a chain, sign and chain, and that's called a pseudo-form. And this stuff is very well known in numerics, but in continuous time is less known, but it's fundamental, as you will see later. So, and then you have operations. These objects are this object that you can evaluate on line, volume, etc. And then you have three things. First operation is the wedge. What the wedge does, if you gave me a K form and an L form, this object spits out an L plus K form. L and K are integer, right? So if I give you a 1 form, is something you can evaluate on a line, and you give me a 2 form, something you can evaluate on a surface, you take the wedge, you get something you can evaluate on the volume. That's the idea. And then what you have is a topological operator, which is related to space, to how the domain is related. This is Stokes' theorem. You know, in mechanics, you what are all these names? I always forget. Green, and all these different. It's just one theorem. It's Stokes' theorem. If you understand these things, you don't need to learn all the theorems. You have one theorem, which says that if you have whatever number n you have, the d of that, which increases, oh, I haven't said that, yes, this increases the dimension, you see? If you have a K form, you get a K plus 1 form. So if you have here a K form, this is a K plus 1 form. So you can evaluate it on something of dimension K plus 1. And you see this is a boundary, which is if you have a 3D volume, you take the boundary, you have a two dimension. So this is it. And forget about the E star is a technical things that it's not important here. But it's something you knew already. But it's in this framework, it's very clear, it's always the same. And the last thing which is important is metric. Everything I tell you here is independent how much you stretch space. Nothing to do with it, nothing. Okay, so people confuse this. It's absolutely not clear in standard engineering that is nothing to do how you stretch space. This is what it has to do with stretch space, because it's something that related says, if you give me a K form, I can associate, in a way, giving you this structure star, I can give you an n minus k, where n is the dimension of the domain you are in. So if you're in 3 dimension, you're giving one form, the odge of this one form is a 2 form. If you give me the odge of the 0 form, is a 3 form. If you give me the odge of the 3 form, is a 0 form. Okay? It's always, the sum is always the dimension. And this turns out to be an inner product. The generalization, you know the matrix, you know the symmetry of numbers that you use. You have a vector here and a vector here. You have the inner product between this vector and this vector. That matrix, this is the counterpart for PDEs. That's what it is. The inner product is this structure. So you have these two structures. You have the matrix structure, which is the inner product. okay, the Hilbert structure on the space use, and then you have a duality between these two variables, okay, which is the Poincare dual product. And then if you go to complexes, which are normally done in vector calculus, you always see this, you know, rotational, you have the gradient, and you have the rotational, and you have divergence, and it seems like this is like a circle. It's absolutely not a circle, okay, and the problem is that using this notation, you lose completely the mixing between what is topological, what is metrical. If you want to discretize, can you do it without losing this structure? Everything is lost. And in fact, instead, if you realize that this is not a circle, but is a line, actually there are two lines. There's one line going like this and then one line going like that. Okay, and then you realize what that means in the language I told you, which is this. This is called the complex, okay, which is just a bunch of numbers, but you see it's, if you have a function is a zero form, you can evaluate it on a point, I told you before. A vector field is something you can evaluate, is a vector field is, you can associate, you can represent it with something of one dimension in some sense, okay? And so like this, and you can go on to infinity. In our case, you don't need, because if you're in 3 dimensions, you only need to go to 3. But this is what it is. And then you have something which goes the opposite direction. By doing that, you also understand, as I told you, the Hodge goes from form to pseudoforms, that these are forms, these are pseudoforms. And there is something even more, which is actually in the dual field paper is not written like this, and I was not happy that it was not written the way I wanted, is the Hodge star is not geometry, is energy density. This is done again also in physics. Hodge is not geometry, is energy density. The geometry is given by the energy density. These Hodges are not the same. That is topology, that is geometry. This is how physics works in general, really. This is the structure of physics. And if I want to talk about power, then I can decompose this, power densities. This would be power density, because if you have a surface, you want to look about the power that goes through a surface, you have to integrate something on that surface, right? So the object you integrate is the surface is two-dimensional. What can you integrate two-dimensional? A two-form, right? So you need something which is a two-form. So power density through a surface is a two-form. Actually, it's a two pseudo-forms, because you need to integrate independently of the orientation. Okay? And then in the volume, that would be a three-form. So basically, you see that this would be the effort, this would be the flow, this is the pairing, the duality pairing, this is V, this is V star. That's it. Everything I said about the composition fits here. Okay? And this is the pairing, the natural pairing about the forms. So you see, the decomposition I gave of vectors and duality vectors can be brought to PDEs. And if you take an example, the energy density, what is energy? If you take a volume, suppose that n is 3, but this is true for any domain. This will be an n form, because you can integrate it on a volume, so it will be a 3 form if you are talking about the energy. And suppose that the energy is function of a L form, okay, whatever that is, I don't care, okay? But this is energy you integrate on a volume. And then you can take what is called the variational derivative. Okay, the variational derivative, you know that the L was an L form, so if this pairing should give you a change in energy, because time is not changing the form dimension, this should be an n minus k, n minus L form. So this pairing is basically the equation that you eventually get for energy storage. Okay, this would be the efforts and the flow that change the energy in a domain. And then you have the continuity equations basically say, okay, the change in energy is what goes through the surface, n minus 1. This is the flux of energy, which is an n minus 1 form because it's on a surface, okay? Plus the energy which is generated or dissipated in this point of the domain. And if you use these two things together, you recognize the efforts on the boundaries and the flow on the boundaries, the efforts on the domain and flow on the domain. You stick it together, and voila, you have a Stokes-Dier structure. So you have energy storage, which has this duality pairing I said before. Then you have the domain, internal domain energy, and you have the boundary. That's it. It's exactly the same as VV star, but now for PDEs. It turns out that this is not enough you want to do to elasticity, because this needs to be tensor valued. Okay? And without telling you what that is, just want to give you again an intuition of that. It turns out that we said this is the energy storage, we just need to use abstraction. That's what mathematics gives us. So you just have to say, okay, this is a pairing. What is V and what is V star? That's all you need to do. Because if you know what V is, then you'll know what V star is going to be. Okay? And it turns out that these V are tensor value forms. And in fact, by this equation, you will recognize what precisely this is. Okay, this is all in the paper I cited before. Intuitively, why do you need it? Take a disk which is spinning in a fluid. Okay, if you use forms and you calculate the form on the boundary, it's basically a projection. You will lose information about the tangential motion. Okay, so basically this would be fine for Euler equations, so to speak. But if you want to have a zero slip condition on the boundary such that the disk moves, the fluid starts to rotate, then you need to also have a component which is tangential. You do it with tensor value forms. And in fact, it's very natural, because what is called the traction force? The traction force is an integral, okay, which is, you cannot always do it in differential geometry. It needs to be not curve the space, by the way. It's a surface integral of stress. Okay? A surface integrals means two forms, right? We know that. But of stress, so it's a force velocity. So the value of that form is a velocity. In each point you have a force on the surface. Okay? And in fact, stress is a map from a plane to a force. So it's something that eats two directions. They indicate the direction, the orientation of a plane, and spits out a force. That's what stress is. So that's naturally what it is. And in this paper, everything in all detail out there. I will close with discretization very briefly. All this, why is all this useful? Not only because it gives you insight in a complete general way to describe physics, but also because it gives you the best way to do discretization and numerics. Okay? Because what is physics is all about this form stuff, K-form. What you can do is what is called the reduction in topology. In algebraic topology, you can basically, and this goes to numeric stuff, you can basically decompose space with kind of pyramids touched to each other. When you do the what do you call it, the gridding of your space, the decomposition of the space. This is what they call reduction. And then you have what is called interpolation. I use the finite element. And when you do interpolation, you basically go again to a continuous situation. But what it is geometrically are all vectors. So these are vectors, but just infinite dimensional. But we can take an analogy. So omega k is this vector. Okay? The set of possible things I can represent on my reduced space are the bases spanned by my polynomials is a subspace. So basically, omega bar is just a vector there. And this process is just nothing else than a projection on that vector space. And by doing numerics, of course, we complete an error because we lose information. This is no. But the geometry is clear. It's just a projection. Okay? And it turns out that if this property is satisfied, for example, like it's done in Fick, it's called the cochain property, then you have topologically preserving, which is called structure preserving. But what do you mean with structure? What structure are you talking about? Topology. Not topology. That's what you're doing. And then you can also, you can preserve this, but you can preserve also the single parts. Okay, and this is, for example, some of the methods that have been developed also in Delft. You can preserve both of them. And then you have this conforming operators property that, for example, Whitney form have. Now, the problem is that, and this was something that was done in the past, that if you, the problem is this guy, is the Hodge, is the metric, is the energy density. Why? Because if you have a form, this is a pseudo form, I told you. If you have a form, you take the Hodge as a pseudo form. But if you discretize it, you know, it's known that this would be, for example, these things, and then the dual would be the dual objects there. And the dual object has a different structure. It is not the same boundary. So if you want something which you can be interconnect to other things, is not clear. You would like to have the same kind of mesh. Okay, the same kind of mesh. So this is creating a problem. And this is due to the metric structure, energetical structure. And this is the crude idea of dual fields. You say, you know what? Every time you have a field, you double it. If you have a field omega, which is function omega dot is equal to something where as an Hodge here, Hodge omega, you know that this would live in a different space. Right? Because of the reason I just said. So what do you do? Well, let's define omega bar. And then I say omega bar, in this equation I will write omega bar. And then I initialize my system on the same mesh. And I do it for the primer and the dual on the same mesh. And once I initialize, you go forward, you have always the same mesh. And if you do that, you have a primary system, you have a dual system, no odge, at least in this strong form. Okay. And then you see eventually that this will be the geometry. Then you have this will be a dual system, will be a primary system. And then you also recognize something which was for the paper of duality. I wanted to write it there, but we will write it. We're writing with Frederick a paper really on the physics of this, because this is much deeper than numerics turns out. This odge is not geometry. This is the density of this energy. This is the density of this energy. And only this shows an enormous amount of information about how physics actually works. And it's generalizable to this. And what it actually does, these things, is that if you have this, you project it initially, the initial conditions. And of course, your physical system will integrate, will move around this space. But what you actually do with structure preserving is that you always have the right projection on this subspace. And I think for the practical side, okay, there is a lot of work which will be done. I just go very quickly on this. And I'm glad that Harry is here, because of course he's been could supervise Luke very, very strongly. And just very briefly, so what Alexander has been working, I will not kill your presentation, is just working on smart materials. So we'll say something more about this. And Flo, I don't know how much you will say about this, but he's been working on smart material, integration of smart materials and sensing. Luke has been working on the experimental side of the story, so in the wind tunnel. This is Harry's baby, I would say, more or less. Is the wind tunnel, and we thanks to the amount of money we had, we could buy this helium soap bubble generator, which is a toy of 200 eventually we paid with all cameras. I think it's 200 to 150,000 euro. So it's an expensive toy, and we had a phenomenal setup. More will be said later, which was used then to do some particle tracking, as we'll show you later. And Ricardo is not here.
He's sick.
Are you kidding me?
I will present a part of this. I got some info of him, so I'll present shortly. But he's
because he had very nice results. You show this stuff? Okay, good. Ricardo has been actually building the setup we use in the tunnel. You could create all the angles. It's a phenomenal setup. And this is a video which we are preparing, a very nice video that will show the whole project. To close up the project is a very expensive 20,000 euros videos, but it's going to be very cool. So what's next? And then I'll conclude really. So theoretically, I am triggered. These are just few of the things. I have a lot of things that I want to do. First is a wave representation of Navier-Stokes. I really see that there is a lot to be said about scattering representation of Navier-Stokes. I think that will give you an insight on turbulence and other stuff. Machine learning for control, this is more Federico's work, is now teaching on my behalf. Numerical solid fluid interaction, this what Ferrami will show some of the things is really paradigm change. What we did, and to bring the moving boundary really to numerics, because we haven't done it yet. We have conceptually solved it, but needs to be done. And there is a number of other challenges. From engineering point of view, I would like to really synthesize new wings, thanks to some of the concepts that came up, and possibly then test it again with the beautiful setups and infrastructure that would be bought. So. Of course, a new robotic burst eventually, which is going to go even better, working better than the one which we have. So concluding, I want first to cite again Albert Einstein. True knowledge comes with deep understanding of a topic and its inner working. And far too little attention is given in engineering about this. You just learn tricks very often in education. Education is going in a direction which is very irritating and worrying me, as we were discussing during the lunch. Because this is not what is taught. In academia, this is what should be taught. Not the tricks, but why the tricks work and how you can change them to make them better. And in Portwings, I think we did substantial contribution. I'm very, very happy and proud of the team that I had the pleasure and honor to work with. And we discover new tools where needed. By this discovery, due to discretization, we found out some new concepts in physics which were very useful and are still working on. port-based things has been the driving thing. So, I mean, the vision that Arjan and Bernard put, also driven by by bone graphs originally, and Painter's work is something which is, I am absolutely convinced, and a theoretical physicist of caliber of Fredrik, I think, agrees with me. In the future, physics will be taught like this. Just people don't see it yet. And inside, I brought two new challenges that will be tracked next. This is the last sentence, and then it's really over. Epistemological growth is not about solving a problem. I'm repeating what I just said, but understanding why and how to solve it. And this is what education, academics environment should be, and this is not the way it's going. So I'm very worried about it, and this is something that should be changed. Thank you very much for your attention. Sorry for being late. Any questions?
So I guess at least just a remark just on the last thing. I guess applied mathematics is a little bit different, of course, with that.
Yes.
Of course, you have to prove. You have the tools to prove things.
No, but I mean, I'm talking more about physics and engineering. If you engineering is something that you need to work with reality. You need to understand things. I mean, this is not true. This is true for every academic thing. So in academia, if you go to University of Applied Sciences, fine, you learn tricks. Yeah. If you're in academia, you should know what are those tricks, why they work, how they can be changed, and academic people should know how to work with abstraction. Yeah. Otherwise, they should not work in academia. That's my opinion. Very strong on that, because I see that students now have difficulties to understand what a vector space is, and this is really worrying. Any other questions? Yeah? Thank you very much.